Okay, I'm going to go ahead and move on then. So this is the next one is the substitution lesson, which is O3 subs. This is going to be the biggest leap. So please ask questions if you have difficulties with it. Okay, so I'm just going to write this to substat.k and open that buffer. And all of the calculs I'm going to replace with substance. And I'm going to peek at my solution just to refresh myself a bit. Okay, so we want to be able to put variables into our expressions. So if we look at the tests for subs, we have, now we have this last expression here, which is A divided by B times C minus D, right? So first we want to be able to still do normal calculator things, but we also want to be able to do things that include variables that are somehow defined to be other values, right? First, make sure that subs compiles like this. Okay, so to add variables to this, we need to add something to the integer domain sort, which allows us to actually type something like the letter A as a variable or something like that, right? But you're not allowed to extend the integer domain sort because it's a hooked sort, and the backend is supposed to treat it specially. And so we're going to have to change the name of this sort to IX, basically. So I'm just going to go ahead and do that globally. And then I'm also going to change the name of bool to boolx. Okay. So now we have IX and BX, which are integer and Boolean expressions respectively. And I'm going to change this val to X to say this is the sort of expressions, it's both of these types of expressions. So not much has changed, except now if we try to compile this, it's going to fail. Well, I think it's going to fail. Let's see. Yeah, and it fails because these rules down here have a variable I1 on the left-hand side, which K thinks is an IX, but on the right-hand side, we're asserting that it's an integer by putting it under the integer module. So somehow we're saying, hey, this is an IX and it's an integer, and there's no sort that relates those two sorts. So we need to subsort into the IX the integers so that K knows that, hey, every integer is actually an IX and every Boolean is also BX, right? So now we can compile this, and these rules will now compile correctly. It will say like, okay, the sort is integer on both sides because the sort over here is assorted to be integer. The sort over here is asserted to be IX, and integer is the smallest sort, so it has to be that sort. And we can actually run programs now. So this first one, which is just 3 plus 3 is less than 8, we can still run and immediately get the true out of it. We've just basically made a slightly larger sort above integer called IX that we then can evaluate down to integers. Okay. Okay, so now we want to have some concept of a memory that we're storing. Well, let's see, do I actually have a memory at this point? Yes, I do, sorry. We need a concept of a memory, so which means we need to explain what these configurations things are, these K tags and configurations are. Because you notice in the output here, we have this weird K tag, and then this thing right here, and then this K tag right here. And actually, K is just inserting the kind of the default one for us because we're not declaring a configuration. But I'm going to go ahead and declare one now for being able to make progress. So this is basically, this is a little different than the default one K is giving us, but this will do for our purposes. We're saying that we're expecting that every program we parse is going to be some expression, which means it's going to be some IX or some BX, for instance, right? So if we compile this, this is basically telling K, this is the state of our execution at any given time. And then we can k-run that and get the same result. Okay. Now we want to be able to put variables in there. So we need another part of the configuration called the memory, which is going to store for us, hey, you know, the value of A is bound to the integer 3 or something like that. So that when we go to say like A divided by B, we can say, oh, actually that means 3 divided by 2 if A is bound to 3 and B is bound to 2. I know it's a horrible explanation, but kind of assuming that there's general knowledge here of how all this works. Now that we have a configuration, though, we need to change these rules to accommodate that. But so here's the basic problem, though. Now our IExps, we want to be able to accommodate variables in them, right? So we have now an ID like this, which is a another built-in to K, which allows us to write variables that are basically lowercase letters. But now these can't be functions anymore because we don't know what the variable A evaluates to or variable B evaluates to. We can kind of cheat, which I'm going to do initially. I'm going to do that initially. Yeah. So we need to define like a substitution thing, which goes down, traverses the entire term, and replaces all the variables with the values that we expect those variables to have, right? So I'm going to say a syntax int is equal to subst I of some IX and some, we'll just start with that. And what we're doing here is defining a substitution function, which will traverse the term and make sure that it's evaluated in all of its arguments. So if you like the idea of algebra and stuff, this is just some sort of morphism. Sounds good. But then we need to tell it what to do on actual integers. So subst I of something that's already an integer is just the integer itself. And subst I of something that's some identifier, we need to tell it what to do for that identifier. So a simple choice would just be anything that's an identifier, we say goes to 0 or something. But we could be a little more clever in knowing, okay, we need identifiers for A, B, C, and D, and just say, okay, if it's A, it goes to 7. If it's B, it goes to 10. If it's C, 3 or something. Actually, let's make B smaller than 7 to keep that division from going to 0. And D goes to 2. I don't know. Okay. So basically, we're just manually building in. A will always be 7. B will always be 2. C will always be 3, etc. So let's try this. I haven't actually tried this yet, so I'm just curious. And it's complaining. So if that works. So complaining, we have to do this. Illegal function. Oh, yes. So now that we have this, these are no longer functions, actually, they're constructors, right? So we have to go through here and remove the function symbol from them so that we can allow the subside function to actually take care of evaluating it. Let's just see if this builds. Okay, so that builds fine. That doesn't really help us to evaluate this last one because we still just get A divided by B times C minus D. So what we need to tell it is, hey, if you see an expression that's at the top of the K cell, run the substy function on that expression. which will go through and actually do the replacements of variables with their values, as well as changing the constructors for our programming language, these plus symbols and stuff, because I removed the function symbol up here. So now they're actually constructors in the sort ix to the integer function arguments, right? So ix goes to substive ix now. So we'll compile that. Oh, yeah, sorry. And we don't want an infinite loop, so we're just going to make sure that this isn't already evaluated down to an integer at the same time. Okay, so can we figure out if this is correct? We have, and sorry about this having to do this sharp token thing. It's just a nuisance dealing with the ID sort itself. But this is the cast format. We're basically just bypassing K's parser and telling it just directly inject the token D for sort ID here. Well, let's see, 6 dot subscript is A divided by B, so that's 7 divided by 2, which is 3, times C, which is 3, 9, minus D, which is 2, is 7. Okay, so we're getting the correct result here by evaluating this. But if we want to change the definition of the value A to, say, 23 or something, we now have to rebuild the entire definition. And we can run it, and we get a different value after adjusting the value of A. And if we want to use other variables like E and F and stuff, they're simply not defined. So let's say we take out the definition of the variable D and run that. Run it. Then the LVM backend comes back and says, hey, I was trying to evaluate the function subst I on the argument D, and I don't have a rule for evaluating that. So here's some unevaluated expression that caused me to get stuck. And you'll notice that it's now exiting with an error code, this 113, instead of returning normally. Okay, so those are kind of annoyances. But we're going to switch from defining this map here directly as part of the substive function and have an external memory that can then be updated later. So we can add things to it and we can update it. And to start off, I'm just going to literally take this definition of the external memory and put it as kind of the starting point here. So this is using K's map syntax, so I have to import map. And now I need to somehow still pass this map into the subst I function. So we're going to say ix k, and we want to get that map in there. So we're going to say, what is it, whatever the current memory is, pass as the second argument to this subst I function. So I'll pass it in there. And now this takes 2 arguments, takes a map as a second argument. And for most of these operations, it just propagates the map down. Like this. And when you have an integer expression, it ignores the map. But if you have a identifier, and we grab that map and we say, okay, look up in the map that identifier and cast it to an integer, which is what this curly braces with the cast around it is. The reason you have to do this is because if you open up domains.md, oh, come on. My brain is real slow today for some reason. And you look up the lookup function for maps, map lookup. You'll see that the sorts returned by it are really generic. So we have polymorphic maps, quote unquote, but really that means you just have heterogeneous maps, which is annoying for doing reasoning and stuff like that. But it means that if you do a map lookup and you expect the result to be some other sort, you need to cast it into that sort. And what will happen is it'll do the map lookup and it'll say, okay, got the item. If it doesn't cast into the correct sort, then just halt execution. So if you would do the map lookup and it would return a bool instead of an integer, it would just halt execution right there and say, hey, something's wrong. can't continue. Okay, so the only difference between the definition we just had, where we hard-coded the map of A goes to whatever, B goes to whatever, into the substy function, and this one is that now we're passing that down as an argument to the substy function, so it can change externally, which will be useful in a later lesson. So I'm going to go ahead and compile this. Oh, parse error. Lovely. What is it complaining about? It's complaining about this extra close parenthesis. Any questions? Yeah, I'll show that in a second. Okay, so here what's happened is we have like a mem cell which has A, B, C, D, which we hard coded into the initial configuration here to just be 23.232, which you see. And then the expression does evaluate down correctly to this 31. Okay, so I'm just going to open up a file called blah, and I'm putting in 1 plus true. And I think it has to be lowercase true, but I guess I'm about to find out. And I'm just doing krun blah. And it's saying unexpected token true because it expects an IX underneath the plus there. Does that answer your question, Marcia? It doesn't even parse. Okay. Okay, so it's still not super useful because we've hard coded this memory directly in here. And also if we wanted to evaluate an expression like 3 is less than A, for instance, it would also have problems with that because it would get stuck at 3 is less than A because we still have that this is a function, right? And so it goes down here to this rule for this function. And it sees, okay, I expect I1 and I2 to be integers, but I2 is not an integer, so it's not able to actually take this rule and evaluate the function down to this. So it gets stuck at evaluating the function less than. So we have to do the same thing to build this substitution-based semantics. We have to get rid of these function symbols here. So now they become constructors instead of functions. Declare subst b function which takes in a map as input to carry the variable values to propagate down. And then similarly, we just take these rules and transform them in this real simple way. And similarly for these rules. And then we have to tell it what to do on the base cases as well. So that'd be the true and the false. Oh, I messed that up. Second. Swear one of these days I will learn how to type. And then we need the true case. We don't care about the map. It just goes to true. And the false case goes to false. Notice we don't have to handle the case of the identifier because we've said up here that only IX can contain identifiers. So we don't allow variables to take on Boolean values. We only allow them to take on integer values. So I'll compile that. And the file blah has 3 less than 0 and it's complaining about something. Yeah. Yeah. So these become subst i's because these are IX presents underneath. And it's happy with that. And so we can run blah. And 3 is less than A does not get evaluated because we haven't told it to actually take Boolean expressions and evaluate them. So we can do that. similarly to this rule here, but for Boolean expressions, which basically is just saying, go and grab the memory and substitute the values that you can into the Boolean expression, but don't do it if it's already simplified, because then you just get an infinite loop where it's attempting to re-simplify like the value true over and over again with substitute. Let's compile again. Okay, yeah, sorry if this is going slow for you guys. I just want to make sure that I understand everything that's going on. Okay, so this is the substitution language. We still have this problem where we have hard-coded values here. We want to be able to get rid of that restriction so that we can update values on the fly and then, have a more flexible programming language. And so that's what the next assignment is going to do, is allow us to do assignments.